Hello and welcome to the third and final video for Calculus of Integrals over Thanksgiving week. So, we are now going to talk about a different type of coordinates known as polar coordinates. So, to introduce polar coordinates, it is worth noting there's more than one way to locate a point. In Cartesian coordinates, which is the standard, commonly known as rectangular coordinates, we measure the distance sideways and the distance up and down to locate a point. However, that isn't the only way we can do it. A different way is to start at the origin, figure out how far the point is away, and then figure out what angle it is above the x-axis, or specifically the positive x-axis. This is called polar coordinates, as we can think of the origin as a pole since we are going around it, and then we are taking a length from the pole and an angle from a starting point to measure the coordinates of a point on the graph. Now, we have a diagram that shows the polar measurements as well as the Cartesian measurements for a point P, which is located at x, y on a graph. What I want you to do for this is think about how many ways you can compare x and y with r and theta. So at this point, I invite you to pause the video and brainstorm any equations you can come up with based on the diagram on the left of this slide and see how many equations you can come up with. So, first of all, x is also the length on the x-axis. So x and y form legs of a right triangle with hypotenuse r and angle theta. If we look at y and r, y is opposite the angle and r is the hypotenuse. So that would mean sine of theta is equal to y over r, or that can be written as y is equal to r times sine of theta. Similarly, x is adjacent to the angle theta and r is the hypotenuse, resulting in the equation x is equal to r cosine theta. The next thing is, since this is a right triangle, we can apply the Pythagorean theorem. So the Pythagorean theorem states that each of the legs squared added will be equal to hypotenuse squared. So this gives x squared plus y squared is equal to r squared, which is another equation. Lastly, we can compare the angles specifically to y and x, noting that y is opposite the angle and x is adjacent to the angle, so the tangent of the angle would be equal to y over x. We can use these four equations to transition between Cartesian coordinates and polar coordinates, or between polar coordinates and Cartesian coordinates. So, let's convert between Cartesian coordinates to polar coordinates. So in this case, we are given x and y values, and our task is to find r and theta. The first equation of importance is that r is the hypotenuse of a right triangle involving x and y. So to calculate r, we can use the Pythagorean theorem. So, with the Pythagorean theorem, r squared is equal to 5 over 2 squared, that is the x-coordinate, plus 5 squared 3 over 2 squared, that is the y-coordinate. Using a calculator or doing this by hand results in r squared is equal to 25, giving r is equal to 5. Our next task is to calculate theta, and as a reminder, we have the right triangle shown at left, where the angle theta has an opposite side of y and an adjacent side of x, giving tangent theta is equal to y over x. Inserting our coordinates, then gives tangent theta is equal to 5 square root 3 over 2 over 5 over 2. From here, everything cancels out except for the square root 3, resulting in tangent of theta is equal to square root 3. Using the main angles on the right triangle then gives theta is equal to pi over 3. Combining these and noting that a point in polar coordinates is written as r comma theta gives us the point 5 comma pi over 3. So we now have converted the point 5 over 2, 5 square root 3 over 2 into polar coordinates, and the result is 5 comma pi over 3. Now let's look at the point 0 comma 7, as this presents a bit of a different challenge. At times it can be helpful to sketch a point that is in Cartesian coordinates when converting it to polar coordinates. In this case, it lies right on an axis. So, using trigonometry and the ideas of the unit circle, we can immediately identify the angle is 3 pi over 2, as each axis is pi over 2 from the nearest axis, and we are going through axis going counterclockwise from the right. We also note that this point is 7 units below the origin, as we can go straight from 0 to negative 7 on the y-axis and reach the point. So that gives us a radius of 7. Combining these ideas, we find that the coordinates are 7 comma 3 pi over 2 for this point. For the next point, negative 4 square root 2 comma 4 square root 2, finding the radius is relatively straightforward as it involves the Pythagorean theorem. A way of shortening the process is to write r is equal to the square root of x squared plus y squared, as that eliminates the need to calculate r squared and then square root the answer, and instead do everything in a single step. Doing so, in this case, results in r equals 8. The reason this point is included is the negative x value with the positive y value makes using tangent inverse on a calculator not the correct answer, as first of all, y over x will give us negative 1. The value for a calculator shown of this will be the equivalent of negative pi over 4. However, if we look at the point negative pi over 4, it will not match where this point is on a graph. In this case, negative pi over 4 is in the wrong direction from the origin, and this point is exactly 180 degrees opposite. This is a cautionary tale where, when using inverse tangent, you need to check to make sure that the angle is not opposite what you have whenever dealing with a negative number. By the way, if both x and y are positive, inverse tangent will give the right result. Inverse tangent is accurate in the first quadrant of the graph. So, with this in mind, we end up having to add 180 degrees, or in other words, in radians, pi, and by the way, for polar coordinates, we will almost always be using radians. So adding pi to negative pi over 4 gives us an angle of 3 pi over 4. So, the coordinates of our point are 8 comma 3 pi over 4 in polar coordinates. Now, let's move on to the last point on this list, and then our last step will be to plot points in polar coordinates. Again, the procedure for finding the radius for this point is pretty straightforward. We take the square root of x squared plus y squared, we square root it, and we get 13. Now, where this one is different, in this case we really do need to use a calculator for inverse tangent, since there is no specific multiple of pi that has a tangent equivalent to negative 12 over 5. Using a calculator to find tangent inverse of y over x, negative 12 over 5 gives negative 1.176 radians. It is approximate as inverse tangent of negative 12 over 5 is an irrational number, meaning a never-ending decimal. If we plot that angle on a graph, it does match up with the direction of the point 5, negative 12, as it is in the fourth quadrant. So this then gives the coordinates of our point in polar coordinates as 13, negative 1.176. So that is sufficient for converting points from Cartesian to polar coordinates. Now let's talk about the polar axis plotting points as well as converting from polar coordinates into Cartesian coordinates. So the reverse of this process. Okay, so first, this axis over here on the right of the slide is a common way of drawing the axis in polar coordinates. For this, we have rings representing each level of radius. Typically this is in integers, which is the case here, where the first ring is a radius of 1, the second is a radius of 2, so forth and so on. And then we have radial lines coming out from the origin at indicated angles. In this case, pi over 12, pi over 6, pi over 4, pi over 3, and on up at multiples of pi over 12. Again, this is the equivalent of a grid in polar coordinates. In terms of how many of these guidelines are given is up to the situation. And technically, nothing needs to be given other than just the main axis, as just like a grid with graph paper, this is for the convenience of the user as opposed to necessary for the problem. Now, let's start out by plotting the point 3, pi over 4. The first thing to do is to identify the angle pi over 4. Now this point has a radius of 3, meaning if we start at the origin, we will count out 3 lines. So 1, 2, 3 lines on the radial for pi over 4. We're going to label this as A since we have multiple points. And so that is the first part of it. That is plotting a point. To convert points from polar to Cartesian coordinates, we reference the right triangle from the first slide. Based on this right triangle, x is adjacent to the angle, r is the hypotenuse, so x will be equal to r cosine theta. In this case, r is 3 and theta is pi over 4, which allows us to calculate x. So x, in this case, is 3 square root 2 divided by 2 if you use exact numbers. A similar process follows for y, except for y is opposite the angle, so y is equal to r sine theta. So, using the same process, we have y is equal to 3 square root 2 over 2, and the point 3, pi over 4 in polar coordinates becomes 3 square root 2 over 2, 3 square root 2 over 2 in Cartesian coordinates. Given that the process of converting to Cartesian coordinates is the same for the other 3 points and only involves plugging in different values for r and theta, that part will be skipped on this video. It will be shown on the notes posted on Canvas. I do, however, want to go over plotting these other points as first of all, the process is best shown repeatedly since this is something that has not been done by most students up to this point very often, if at all. And since, if you look at the last point, there's a key detail that is a bit weird that's worth going over. So let's start out with 5, 3 pi over 2. So the first step is to identify the angle 3 pi over 2 on the graph, which is this radial going straight down from the origin. Now a radius is 5, so we count 5 rams. So 1, 2, 3, 4, and 5. We'll label that as point B. Next of all, the point 2 comma 4 pi over 3 is again a similar process. We identify the radial 4 pi over 3, and we count out a radius of 2. We can then label this as point C. Lastly, we have the point negative 3 comma pi, which has a negative radius. To do this, we first of all identify the radial at pi. Then, instead of going towards the value of the radial, we are going to go in the opposite direction. So we are going to go away from the pi and instead go to the right by 3. So instead of going towards pi, we will go away by 3, meaning 1, 2, 3, and this ends up being the coordinate, that ends up being the point for negative 3 comma pi. As instead of going towards the angle value, we went in the opposite direction. So this summarizes how to plot points in polar coordinates, how to convert points from Cartesian coordinates to polar coordinates, and from polar coordinates to Cartesian coordinates. We will go over more about this when we return to class, as we will start talking about functions in polar coordinates and then later calculus operations on functions in polar coordinates. Thank you for watching. I hope you have an excellent break.